answer?
Yeah, it's probably. Grasp something or.
Because the answer that I originally got,
I don't know if I put anything.
was that. This is what I got, and then I got the second time, and you got
Oh,
the
sweet.
question mark. Hey, Rachel, second
Hmm?
time, what did you get for puzzle points?
2B.
How did you know whether it was students or social?
Well,
How? Because they said so.
where the velocity and the acceleration are the same, it's speeding up, and where they're different, it's slowing down.
But this is from initial to terminal, so you don't have the interval.
Well, you're only talking about the interval, which is 0 to 4.
But that's 0 and that's 4. So you don't know.
You have a graph from 0 to 4, and the graph will be positive and negative at times. Where that segment is positive, on both sides it's speeding up, and where it's also negative on both sides, it's also speeding up, but where the signs are different. Let me show you, I think I have an illustration. I had to rework basically.
Yes,
everything.
okay, mean an A.
No?
Yeah, that's telling us.
No.
Hmm?
Okay.
We all
Well,
agree
under the
to-
intervals,
Her name is Kathy. She's pretty
This is
good.
where it's negative. This is where acceleration is positive. This is where velocity is
Yeah,
positive. This is where it's negative.
It's okay.
So these,
We
this
didn't know
right
what we
here is
wanted.
slowing down. But here they're both negative, this tiny thing. So that's speeding up. This is where they're slowing down again, and this is where they're speeding up again. So if you know where like the x-intercepts are, you can basically work it out. You can do that little thing that he did, where you list out all the points, but I like seeing it visual myself. But you know what, I don't.
So what did you
Also, last night, I got every single problem wrong. I did not get anything right.
On the 2.4 homework?
Yeah. It was 2.4 and 2.5.
2.4 seemed really easy.
I don't know why I couldn't get any of it right. I mean, I had the answer key, but all the answers were so long.
Well, so were the
Maybe they were
calculations.
just, maybe they were just written.
And the answers were like written like you were doing them though.
I don't know.
Rachel, is this what you got for 3A, or was there something else? I only got one.
Give you the integrals of accelerating and decelerating.
I just got the small ones. I didn't think there was any union. You got the.
I got a union on decelerating. 9 to 15. Which makes sense really, because the velocity here is just like 5, and kind of shy of the 0, then it goes to 0. So that is. Also,
9
you
to
had it.
15?
Yeah.
But I got this part wrong. Wasn't here
Well, this is a lot.
this
I was totally not 15.
Wait.
Yeah, I had to redo every problem though, except 9, for some reason. And the only reason I got number 9 right is because I looked at the lecture again with the parts and talked about it. I would basically redo it verbatim.
And then I have 2 questions. This graph for 60.
Yes.
So it's asking for the graph of which this is the derivative.
Yeah.
This can't itself be the derivative.
Yeah.
Like the graph we make isn't the derivative of this.
It's the original graph. It's the
Yeah, you
original
have to do a
graph.
slope.
Huh?
You have to do the
lines.
field.
Slope field, like time field.
The slope field is which direction it's going in, so you go.
Average speed is distance equals rate times time, so the distance
But I
is
can't
36
visualize
feet.
that.
Time is 15
Right.
seconds. 36 divided
So,
by
like-
15. 2.4 feet per second.
That's where I'm struggling with this.
Okay, yeah.
Like I got A fine, this is
See this? So basically what you have here is you have a negative slope that's slowly approaching a constant positive slope here, right? So what you do is you have a negative slope. So you have like half of a parabola that stops at the vertex. So once it stops at the vertex, it goes up at a constant rate, and then it stops again, and then it goes up again. So another half of a parabola. Yeah.
And the only other thing that I didn't get on this was 8.
Okay, I hated 8.
I hated 8 too. I mean,
Okay.
you're looking for the,
I got it though. Look at this. It's basically this, and this is basically the only thing it can do.
But isn't that the graph of f prime, or what did I just say?
The growth of it.
Never mind. The graph of x prime of x.
What?
That's,
Well, you're supposed to just graph function f of x that eats the whole.
I know, but all that's based on f prime of x.
Yeah, graph function.
Yeah, well the thing is you can move it vertically however you want, but what
And that
matters
wouldn't
is that
change it.
what matters is you have these fundamental points of vertex at f1.
Unmuted.
Tan line 3 equals 1, and then it's constantly decreasing, which makes no sense, but you know what, I'll take it.
So where did you start at on your graph? Like, what was your first y value for x? Was it at 1 or 2 or 0?
I think that's right.
Because I drew that one.
Yeah, that's right.
There was one.
Did you do it? Not enough time to get it right.
Oh, you? What do you mean? You had it all false right.
Test release.
I had a little bit Sunday, but then my grandmother came.
I was busy pretty much the entire time, but I was fun.
It's not worth my time. Going to that grade.
I mean, it will.
Oh, I gave
Tuesday.
How many points did they drop?
Class.
You said there's more before.
Can we finish the material, last section?
How much more was it?
We should do that fairly quickly.
You just did that on the other test, too?
Yeah.
Uh,
I need to do that.
Wednesday is a review day.
I hope to justify doing that.
See.
Make sure I understand. Okay, so I left my. Remember when I scanned the thing to send it? I left it out there for a minute. But it's a good thing I had it all in my head. I memorized all the answers. All the answers. They're all in my head. I know this test inside and out now. Yeah, Mondays, rainy days and Mondays always bring me down.
Myself down. So I got a notebook.
That's great.
Yeah.
That's an inferior notebook.
Is that a Carpenter song? Yeah. I was gonna say,
I was up so late last night.
How
Back
late
up.
is it?
40
I
years
finished
ago.
the exit
Oh no.
at like
And she's still at home.
1:40.
Sammy.
Jeez.
I can't tell you how productive I've
Right.
Did you have them for that clip?
Yes, I got applied to college and I applied for 2 scholarships. I
This
wrote
is
an
like
entire
10 plus
amount
pages
of
of notebook paper.
Yeah,
5
mine's like
essays
11, dude. It's crazy.
Well, how
and
long
a million
is it?
short answer questions.
How long
Dude,
is
that
it?
is-
I had Alex help me with 8, so if you all get 8 wrong,
I know,
we
like,
know
the
who
Moorhead
won.
Kane
I
scholarship,
think I get
it
it though.
requires 3
Is that the right
2,000 word
answer?
essays.
I'm pretty sure I'm not thinking about it.
So I
Alex
decided to
said we
get
went
that.
5 different answers for
Is
that
it a law
one.
school?
It's for, no, it's for Chapel Hill and
Duke.
No, Moorhead Kane.
Hey,
Ask Mr. Gaddis what school he went to.
Before we get started, I guess now, Davis, have you turned in your test corrections now?
Let's do that
Yeah.
because I want full credit. I need full credit.
Okay.
Mr.
So,
Gaddis,
yes,
can I ask you a quick question? Because it's the season of college applications for us at the early college, can I ask what college you went to?
yes. I went to University of South Florida in Tampa.
Oh, cool.
There I got undergraduate in math and engineering.
No, I don't
2
know that.
undergraduate degrees. Then I went to UNC Greensboro for graduate.
Cool.
Oh. Okay,
Mason?
so Greensboro, that's over in your neck of the woods. Is that one of you're applying to?
Is he asking me? Oh, yeah, I just applied to Chapel Hill, like,
Fantastic.
over 2 days ago,
2
yeah.
days ago.
2 days ago.
Do you have yours linked?
Mason
Yes.
applied.
No.
All right.
It's like they applied 2 days ago.
So what's let's see. You got left. So
Please, right?
we have a test Thursday on this block of material, which covers sections 3, 4, 5, and 6. We've gone all the way through 2.5. We did that last time. So today we need to do 2.6, which shouldn't take too long. It's on the trigonometry.
Yay.
Basic kind of stuff. Then we added in logarithmic and exponential, and now we're going to add in the trig. That'll be the end of it. So once we get through that, then we can have time to go over any questions you have on the homework that you've already looked at, including also Wednesday will be a review day for the test. Tomorrow, Tuesday, is advising day, so we won't have class here. That's the day, so we won't have class. Then we'll be back on Wednesday for review. So let's go ahead today and do the coverage of 2.6 real quick, and then we can, after we're finished, we'll go back and see what questions you have on the homework that you've already tried, and then catch up on that. Okay? So let's just knock this out real quick. We need to have a derivative. We're going to start over here. We have a derivative of trig functions. So start with derivative sine of x. And we want to figure out what that's going to be. The book tells you what it is, but we'll derive it first, and then you just, after that, you just know it. So what's the definition of derivative? Going back on a good review, what's the definition of derivative? When then h goes to 0, and we're going to plug x plus h into this function, so that would be the sine of x plus h, and then minus, plug in an x, sine of x, and all divided by h. Dash. Again, at this stage, we still have indeterminate, because if h gets close to 0, we got a 0 in the denominator, and if h gets close to 0 up here in the numerator, x plus h is going to be close to x. So sine of x minus sine of x also causes 0. So we still have 0 divided by 0, which is indeterminate. But so we need some way to cancel out that h. But I can't just factor it as it sits, because the h is inside the sine function, so I can't factor it out. So I have to use trig identity. Does anybody remember your trig identity for the sine of the sum of two angles?
Oh gosh.
Yeah. Sine of A plus B is what? Sine of A, cosine of B plus cosine of A sine. What's that? Yeah. So this will be sine of x, cosine of h, plus cosine of x, sine of h, minus sine of x. So that was the angle sum identity. So now you find out why you really needed to know that back in trig. It was fun in trig, but now you have to know it to be able to do this. Okay. Now, what can we do? Well, I see a sine of x here and here, so maybe I can figure out some way to rearrange it so I can factor it.
Okay.
So let's see, sine of x, cosine of h, minus sine of x plus cosine of x sine of h over h. Now let's see, now what do we get? If I factor out a sine of x, I get cosine of h minus 1 over h. Here I get cosine of x times sine of h over h. So I put my h under two different fractions. On this one I have cosine of h minus 1 once I factor out the sine. On this one, once I factor out the cosine, I just have sine of h over h. Now, why would I do all that? Well, let's see. I gotta split up my limit to each factor now. So I apply my limit properties. I'm going to split it across the plus sign and the times sign. Almost done now. Is everyone with me to here? We applied the definition of derivative. We applied a trig identity. And now I'm just doing some algebra. I split up my limits. So limit of sine of x as h goes to 0. Well, h is not affecting sine of x in any way, so that's just sine of x. Limit as h goes to 0 of cosine of h minus 1 over h. Does anybody remember what that one is? That's one that we learned back in the limits chapter. Back in the limits chapter. Do I remember this one? So chapter 1. Well, I know we saw it somewhere. Yes, on page 142. This becomes a 0.
What's cosine of h minus 1 minus? No, I don't think so.
Sorry, question?
I think I'm just stupid here. Because wouldn't that be?
Sorry, what now?
Oh gosh.
It would be a negative, right? Okay, so I'm going to factor minus sign out. So it really should be negative cosine of h plus 1, and that makes a negative on the outside. But then that means I have negative of 0. What's negative of 0? Still 0.
That's 0.
Now, h approaches 0, cosine of x is just cosine of x because h is not affecting the x at all. And then this last one out here was also on the same page. That's a 1.
It's cosine of x.
The answer comes out to be cosine of
Yeah.
x.
It's okay. It's a game.
No, it's not okay. We'll never be okay.
Derivative of sine is cosine of x. Let's take a look at the graphs of these two and make sure it makes sense. Graph. So I'm going to start here. Hopefully you remember the graph of sine of x. Sine of x comes to the origin, goes up, reaches a peak, comes back down, reaches the minimum, back up. So this is y equals sine of x.
Negative 1 equals.
If I was to draw the derivative graph of it, okay, so we've done this before. We look at tangent lines. So right there, the tangent line is a 1, so I'm going to put a 1 right there.
That's
And
cool.
then right there, the derivative tangent line is a 0, so I'm going to put a 0 right there. And that's a tangent line of -1, so I'm going to put a -1 right there. That's a tangent line of 0, so I'm going to put a 0 right there. That's a tangent line of 1, so I'm going to put a 1 right there. So my graph does this.
That's awesome.
So this is the y prime, and y prime is equal to cosine of x. Interesting. So what do you think about the derivative of cosine? The next question is, what about the derivative of cosine? So now we know the derivative of sine is cosine. What about the derivative of cosine?
Second, is that sine?
Well, it seems like that ought to be sine, but it's not quite sine.
Not quite sine.
Is it 1 over?
Almost sine, but it's not quite sine.
Uh,
So let's start with y equals cosine of x, which we know what that looks like.
that's a snake.
There's y equals cosine of x, sort of. And now let's graph the tangent lines of that.
That doesn't look balanced to me. Like at all.
So here the tangent line slope is 0, so I'll put a 0. Right here the tangent line slope is -1, so I'll put -1. Then I have a tangent line slope of 0. Then I have a tangent line slope of +1. And a tangent line slope of 0. So there's my graph. So yeah, it's related to sine of x, but it's not y equals sine of x. What is it actually?
If it's negative sine of x, I'm gonna
It is
like.
negative sine of x.
It is the negative of sine of x. That's exactly right. Negative of sine of x.
Freak out.
You should be able to prove that by the same method we just went through. Over here. Okay? Instead of starting with sine of x, you start with cosine of x. How's that going to look different? I'm not going to spend a whole lot of time, but I'll just, it's very similar. The only difference is this identity is different. That's what changed it. So if you
I get it.
Okay, so cosine of x here, cosine there, cosine there. So cosine of the sum of two angles, cosine of the sum of two angles. You better remember that identity. The rest of this is going to be wrong now, but it'll get you started so you can do it yourself if you had to, which you might have to on a test or something.
Oh.
One more time, on the test, you'll need to be able to do a couple of proofs of these derivatives that we've been coming up with. I can actually do them all, but some of them. Okay, so what is the cosine of the sum of two angles? What does that identity look like from trigonometry? Cosine times cosine, and then minus sine times sine. So that was the identity for the cosine of the sum of two angles. So it has a difference in it rather than a plus, and it has cosine, cosine, sine, sine. Okay, so now the game is still the same from there. It's a matter of getting things to match up so you can factor and use your identity theorems that we learned earlier for sine and cosine on page 142. So the rest of the game is essentially the same. You ought to be able to see a cosine here that you can factor out, and then you're still getting the same idea. So I mean, these first two and that cosine will match up and factor out a cosine and leave you something involving cosine of h minus 1, and then you'll have a sine and a sine of h over h. That gives me something. So you're going to end up, if you go through the whole process, you'll get a negative sine of x out of all of that. That wasn't too bad. You should be able to do that on your own. The book doesn't have it in there. They just did sine, we did sine. Cosine is the same game, but you all see that it's going to be similar now. You see the grouping of these, the factor of cosine, and the grouping of those. Okay. Next up, go back over here. What about tangent?
What about
Derivative of tangent of x. There's a couple ways to do this one. You can use the definition in the same way we just did, meaning you would have to know the angle sum identity for tangent, which I don't off the top of my head remember. I think I could come up with it fairly quickly, but I have another way we could do it. Any other suggestions besides using the definition like we just did that you can think of?
Well,
yeah, let's rewrite this
yeah,
as
yeah.
derivative of sine of x over cosine of x. How are we going to attack that? We need to use the quotient rule. That's right. We're going to have to use the quotient rule. So this is now a quotient. I got to do the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over the denominator squared. So exactly right. I do the quotient rule.
I feel like I had to prove this somewhere.
And what's the derivative of sine of x?
Cosine of x.
Cosine of x times cosine of x minus, I've got sine of x times derivative of cosine is negative sine of x But what's cosine times cosine minus sine times negative sine?
What's that supposed to mean?
Yeah, I'll write it down so everyone else can see it. Cosine squared, negative times negative gives me positive.
Yo.
That's 1 over cosine squared And that's also can be rewritten as an identity from trig.
He just Pythagorean.
Cosine is an identity for area. Secant, that's right. So this is secant squared of x. This is your derivative of tangent. Any guesses what the derivative of cotangent is?
Because
Cotangent disc.
Did we all follow the tangent derivations?
Mm-hmm.
Quotient rule, and then we simplified, did some trig identities, the Pythagorean trig identity, the reciprocal identity for secant.
Don't tell me, is it going to be
What about cotangent? Any guesses? Oh, cosecant. That's correct. And it's got to be like over here. When we did derivative of sine, it was cosine. The derivative of cosine, it was negative sine. The derivative of tangent is secant squared. The derivative of cotangent, if you go through the same process, is negative cosecant squared.
Hey, this isn't that bad.
Symmetry to that. Okay, let's move over to the next board. We'll do secant, derivative of secant.
I was drawing Venus. Oh, dang. That's special effects.
There's a couple ways to do this one.
What the heck?
And I could try to go with the definition, but that's going to get messy, so I'm going to try doing something else. Write secant as 1 over cosine and do a quotient rule.
Oh, snap.
I'll do this. Or, just to practice, I'm going to write it as a chain rule.
Hein?
Oh no.
It's a Hein rule. I'm gonna kill you. I have to get my Germanic roots out, you know? Hein.
That's going to be messy. That's gonna be messy. We'll try it this way. I don't know if this is the way I want to go or not, but I'm going to try it. So how do I do the derivative with the chain rule of this?
Well, f of g of x is equal to f prime of g of x times g prime of x. Yeah.
Yes. So what we did last time is we saw this was like, we might call this the inside, we'll call it maybe u. And we had to take the derivative with respect to u. So
Make it f, please.
f du. And f is this outside function here. This is f.
I'm pleased.
That would be what? -1 times u to -2. Y'all agree with that? Well, we got to still do the derivative of u with respect to x. Okay, that's just negative sine of x. Okay, so let's see if we can fill that in over here. So the first one is the derivative of the outer function with respect to the inner function u, which is -1 times u to the -2. -1 times cosine of x to -2. And then times, and then the derivative of u with respect to x is negative sine of x. Well, the negatives multiply to positive, and I end up with sine of x
Over cosine
sine
squared.
squared of x. Now that can be rewritten a little more cleanly, and that's fine, but here's a little bit nicer way. We can split this up into, let's see, 1 over cosine of x times sine of x over cosine of x. Over cosine is secant times cosine is tangent. So the derivative of secant of x is secant times tangent of x. Any guesses over here real quick? Derivative of cosecant of x?
Just give up, y'all.
Guesses? There's been a certain symmetry all along here. It continues. Negative cosecant of x times cotangent of x. Right.
Swag. Scientific wild.
Okay? But a quick example of one of these, and then we'll do we gotta still do inverse trig functions.
Oh my gosh.
So maybe an example. About the derivative with respect to x of tangent squared of x to the third plus 4x. Now this, folks, is a step up by a level. This has 3 levels of chain rule. Okay, I don't know if you see this. What is the last operation that you perform on this? If I told you x was 7 and asked you to evaluate, what would be the last operation you perform?
Is it the square?
Square would be the last thing. What would be the second to last thing you perform? Tangent. The first thing you perform is everything in here. So y'all see 3 levels of what we call chain? This is my innermost, so that's my first, that's deepest, and then so this is my first inside, and then the tangent is my second, and the square is my third. That's just order of operations in algebra. But in derivatives, you reverse it. You peel the onion back. So I'm going to look at the second and third. I'm going to ignore this part for a moment. I'm just going to look at these two. This is like a chain rule right here. My outer function square, and my inner function is the tangent. So the derivative with respect to u of f, that's a square. We got a square here. This is the square. That's 2 times u to the 1. But my u function this time is tangent. So this is we'll call this one u1 right there. That's tangent is my u1. u1. And then the derivative of u1 with respect to x, derivative of tangent is secant squared. Problem is that what's inside there isn't really an x. It's other stuff. Here's where we got to do another level of chain. So let's write that down so far, what we have so far, and then we'll do another level of chain. So this is equal to 2 times tangent to the first power of what's already there, x cubed plus 4x, times, then times the derivative of the tangent, which is secant squared of x cubed plus 4x, times, now I got to do a derivative of the inside stuff.
Wait, is he already layering the chain, or?
Now we're doing the chain right now. This is a 3-level chain instead of a 2-level.
We're already tripling the chain?
So this becomes 2 times tangent of x cubed plus 4x times secant squared of x cubed plus 4x. And that becomes just simple power rule, 3x squared plus 4.
Okay, I don't get it.
Here's the derivative of a 3-level chain involving tangent. Notice how, because the tangent had a power on it, because the tangent already had a power on it, it remained in the problem because you used the power rule, 2 times tangent to the first power, which we saw right here in this u. But then the derivative of tangent itself. So I did a derivative of the 2 right here, 2 power. Then I did a derivative of the tangent, which is right here, secant squared. And then I did a derivative of the inside stuff. 3 levels of doing derivatives there. Got all of that? So you need to be able to handle more than just a 2-level. You got to be able to handle a 3-level, maybe even a 4-level. But certainly a 3-level is something you ought to be able to see and do. Okay, so that's the trig, basic trig rules. Now we can do the inverse trig rules, and
Is that the answer?
we'll switch that question again.
Oh my god. Is
Question.
that the answer?
That's the answer.
Oh my gosh.
What?
I was doing the chain rule for 2.4 and all the answers were so long and I just felt like I was in a void of understanding.
Okay. Well, do you feel better that you were doing it correct now that you see what the answer should look like?
Not really. But I can just follow the motions.
Okay, so now inverse trig. So I want to figure out the derivative of inverse sine of x. And again, trying to use the definition directly is a real mess. So I'm going to change gears on this one.
No, he just moved. Just kind of walked to the side.
I'm going to say that this answer is that I'm looking for is equal to the derivative of y with respect to x if y equals inverse sine of x. So if I can find this symbol, dy by dx, derivative of y with respect to x, then I will have found this derivative I'm looking for. So I could, again, if I just take the derivative of both sides of this equation, and I'm right here where I started. But I don't want to do that because that still puts me in the same position. So what I'm going to do is I'm going to rewrite this equation as sine of y equals x.
How do we do that?
Definition of inverse sine. All right. So inverse sine and sine are inverses of each other. Okay, so now I can do implicit differentiation.
It's a mind blow. I understand. Silly.
Okay. Well, the right-hand side is easy. The derivative with respect to x of x is just 1. What about the left-hand side? With implicit differentiation, what do you have to do there? First of all, what's the derivative of sine of y? Cosine of y is right. That's right. So derivative of sine is cosine of y. But when you do implicit, you have to visualize in your mind that this y right here, think of that as a function of x. So I have to now take the derivative chain rule. I have to do a chain rule derivative with respect to x of y. We've done that implicit differentiation before. So this becomes cosine of y times, and the derivative with respect to x of y is just y over dx.
Cozy.
Y over dx equals 1 over the cosine of y. Now, the only drawback, the only difficulty right now is I started with a nice little function of x at the beginning. Inverse sine of x is a function of x. Now I've got a derivative. I've found a derivative that's not a function of x. It's a function of y. So I want to convert back. That requires a little bit of knowledge of right triangle trigonometry. So what does this statement up here means? I have a triangle. It says that when you do inverse sine, you're getting an angle. So the angle is y. So this angle right here is called y. And it's telling me that the sine of that angle y is x. So that would be x over 1. So these two pieces of information, they're the same thing. They give me that right triangle. Does everyone understand that right triangle?
Mm-hmm.
Sine of y equals x. Sine of angle y is equal to x. That means this adjacent side is the square root of 1 minus x squared. By Pythagorean theorem. So now I can bring this back down here. What is the cosine of angle y in that? So I'm looking for cosine of angle y. What is the cosine of angle y in that triangle?
The square root
Of
of
one.
Root of 1 minus x squared over 1, which is a square root. This is just square root of 1 minus x squared.
Based off what the sign of x is. Really?
So this is what I was looking for. dy by dx is the derivative. So we're saying this answer, derivative of inverse sine of x is equal to 1 over square root of 1 minus x squared. Okay. Any guesses what the inverse cosine derivative looks like?
It's 1 over. Oh crap. Oh crap.
Negative 1 over square root of 1 minus x squared.
It's the same thing?
Well, same thing, but with a negative sign.
Sure. I'll take it.
The reason is, I think I see where you're coming from, but if you go through it, the triangle is going to change because you're starting with not inverse sine, but inverse cosine. So these two sides are going to flip-flop. And then when you do a derivative of, you're going to be doing a derivative not of sine, but of cosine. The derivative of cosine is going to give you a negative sine. And when you go through your triangle, you'll get the same, because these are flip-flop, but you're now doing sine, so you're still getting the square root of 1 minus x squared, but there's a negative involved because you're doing the derivative of cosine. So that comes out fairly nicely. What about inverse tangent? Let me give you a moment to see if you can figure this one out yourself.
I already found it out, Dale. I'm years ahead of you.
Well, I'll give you a hint. It's the same game. You start off by saying, well, to find this derivative, it's dy over dx if y equals inverse tangent of x. And see what you can do. Take a minute or two. If you can work your way through in a similar fashion what we just did for inverse sine, but do it for inverse tangent. A minute or two on your paper. So you should have been able to rearrange your equation using inverse functions knowledge, and then use implicit differentiation again, where the derivative of tangent of y is secant squared of y, and then because that's a y, not an x, you got to do implicit and get dy by dx. Solving, you divide by secant squared, which is the same thing as cosine squared of y, and then using your right triangle, back up here, get this right triangle, and that gives me what cosine is. And then you square it, you get 1 over 1 plus x squared. So we have learned from this that the derivative of inverse tangent is 1 over 1 plus x squared. Yes, Jacob.
For the book, it has to be 1 over 1 minus x squared.
Cool.
Inverse that.
Sure.
Page 29.
Oh no, that's something. Oh, you're on. Okay. You're on hyperbolics. So inverse tangent is on page 225. Okay. So for everyone else's application, page 225 has your inverse sine, inverse tangent that we've done, and then we inverse secant is right there. To save time, I'm just going to say inverse secant is the same game as what we just did, but there's something special about it. We need to talk about that in a moment. What I want to mention to everyone else is, after we finish these three, the next part of this section starts on page 227, is hyperbolic functions. And I'm going to just mention them briefly in a moment, but we're not going to be expected to know them because we don't have time to really get into them. Sadly, they're good things, but they can be handled otherwise. But back to inverse secant on page 225. Let's do that real quick, and then we'll be done with it. So, first question I want to ask: any guesses what inverse cotangent, derivative of inverse cotangent would be? It's not in the book. So I'm just asking you. What do you think the derivative? We've got inverse sine and inverse cosine. We just did inverse tangent. What do you think the derivative of inverse cotangent is?
What is it, negative 1 over 1 plus x squared?
Yes, it's negative 1 over 1 plus x squared. That's a good guess. Okay, good. So the derivative of inverse cotangent is negative 1 over 1 plus x squared. Next, I want to discuss, without taking a lot of time to derive it, it's not hard, you can do it yourself, but I want to just spend the time, instead of deriving it, I want to spend the time discussing why there's an absolute value symbol in the derivative of inverse secant. They tell you on page 225 that the inverse secant derivative of inverse secant of x is 1 over absolute value of x times the square root of x squared minus 1. 1 over absolute value of x times the square root of x squared minus 1 is derivative of inverse secant of x. Now, again, the plan to derive that is the same as we've done over here. You an equation, you solve it the other way, and then you do implicit differentiation. And then you get a right triangle, and so the process is identical to what we've already done twice now. But why does this one have to have an absolute value? And that's not entirely obvious. Even if you go through it, you'll just get an x in your answer and not the absolute value. So we need to talk about it. for a moment. So if you take a graph of y equals secant of x, so this is just a quick review of trig, you get something like this. And then y'all familiar with seeing that kind of graph for secant of x, y equals secant of x, and then repeats? Oftentimes when you're learning it, you talk about, because that's reciprocal cosine, you draw in the cosine graph like this. We're doing that probably in trig class or something. Okay, well now let's talk about inverse secant. To do inverse secant, this is not a one-to-one, the black graph is not a one-to-one function, nor is the red one for that matter. So we cut it off between here and here, and that's going to be one-to-one now. So this is our restricted domain, and that allows me to create the inverse secant function. So let's see.
Oh my gosh, I remember this. I remember.
So what you're doing is you're visualizing, this is the restriction I just made right here. But we've switched the meanings of things. So I'm taking this picture and doing a mirror. So that's inverse secant. This is the graph now. This is the graph of y equals inverse secant of x. And here's the observation I want you to see. So first of all, that was just a quick review of the secant graph from trigonometry and the inverse secant graph from trigonometry. What I wanted you to see from this, by the way, this picture's in the book. I mean, it's on page 226, I think, is a picture of inverse secant for you right there in the book. What I wanted you to see is, what can you tell me about the slopes of the tangent lines on inverse secant? So this is derivative is the slope of the tangent lines. Derivative slope of the tangent lines. So the tangent line, for example, there is a pretty big positive number, and then a less positive and less, but it's always positive right there. We all agree that's always positive tangent slopes. What about over here? These are small positives, small but bigger positive to basically almost infinity there. But notice that they're positive slopes either with x being positive numbers or x being negative numbers. It's always a positive slope. If I don't put absolute value here, then when x is negative, I'm going to have a negative slope. You all follow that? So at x equals -2 back here somewhere, if you plug a -2 into this, you're going to get a negative slope unless you have absolute value. So this absolute value is a kind of an extra add-in that the others don't have. Others didn't have anything like that because it all worked out fine. But on inverse secant, because of the way we had to restrict the domain, and you got always positive slopes, now you've got to put in the absolute value. Okay? All right, so that's the inverse trig and trig. We can do an example, another example if you'd like of this, and then we can also entertain questions on homework. So let's do one question. Raise on.
So just for clarification, did you say that we don't need to know hyperbolic functions?
On the test, that is correct. Hyperbolic functions are defined for you. on page 220, 227, 227. They are interesting functions in that because one is the regular trig functions are based on a circle. If you look at the hyperbola at the top of page 227, you can define what are called hyperbolic trig functions. Has anybody heard of hyperbolic trig or done anything with that before?
Yeah.
A little bit with it? Okay. Well, that's fantastic. Because they're defined based on e to the x, you can actually do the derivatives using the derivative of e. And the derivative of e is fairly easy. What's the derivative of e to the x? E to the x. So I don't personally need to take the derivatives of something, renaming this as something else, and then do the derivatives. I can do the derivative of e to the x as easy as I can do anything else. But so they've got a whole, what they call a starred or optional section on the hyperbolic and inverse hyperbolic. If we had more time, we would delve into that, and but we won't this time because we're short on time. So you do not have to know the hyperbolic and inverse hyperbolic derivatives. But when you leave this class, if someone says, "Have you ever heard of hyperbolics?" you have to say yes. Yes, I've heard of them. Okay, one example of something. What about derivative of inverse tangent of x to the third power?
Oh my gosh. Are we gonna have to kind
What do you think here? We'll need a chain rule, that's correct. So, again, helping you to recognize it. Your inside function is only a two-level chain. Your inside function is, we'll call that u, and then this is your outer function, which we'll call f.
Yes.
So we're going to do a derivative of the outer function with respect to u. So that's like inverse tangent of u. d by du of inverse tangent of u. That's what I'm asking you to do right there. We just did inverse tangent. What is it over there?
1.
Okay, that's the derivative of inverse tangent of u. But we have to do the chain rule, and we have to do the derivative of u with respect to x. So the derivative with respect to x of x cubed, which is 3x squared. So putting that all together, the derivative of f with respect to u is 1 over 1 plus u squared. But u isn't simply u, it's actually x cubed.
Mm-hmm.
And then the derivative of x cubed with respect to x is 3x squared.
Oh, that isn't too bad.
I agree. X squared over 1 plus x to the 6th.
Wow. I can actually spatially conceive this one.
Okay, good. Good. That was a two-level chain. You just had one inside function and one outside function. A little bit easier to see, but you got to be able to handle 2 or 3 level. Okay, so we'll stop there on those examples and let you ask questions on. If you want to do more of these examples, I'm glad to. Or if you want to go back to the homework you've already been working on, let's let's take a few minutes to look at your homework and see how we're doing there. We don't have a lot of time, so let's see what questions you have.
I got everything wrong.
4, number 43, I heard. 2.3, 2.4, number 43. 2.4.
Good for you, man.
Number 43. 2x plus 1 to the negative fifth minus 1 all to the negative 9. Oh my gosh. 43.
Just kill me.
Okay, so this is 2.4, number 43. We're supposed to, does it say find the derivative? Is that what it says to do? We're trying to find the derivative of, what was it again? 2x plus 1 to the negative fifth, like that? Yeah. Minus 1 to the negative 9, like that? Okay. Well, let's start by identifying, again, for derivative purposes, it's like dealing an onion one more time. So you look for the outermost function, and then see everything else is the inner. And then we just keep doing levels of chain that way. So if I do it that way, this is my f function on the outside of everything, and everything inside of it is my u, the first time around. We might have more after that. So derivative of f with respect to u is derivative with respect to u of u to the negative 9, which is negative 9 u to the negative 10. And then I have to do the derivative of u with respect to x. That's d by dx of, well, now here's the problem, folks. We've got stuff going on in there. So I'm going to have, I got two parts to it, a minus 1 and then the other stuff. So I got to do a derivative of 2x plus 1 to the negative 5 minus, and then a derivative of negative 1 is going to be a 0. But how am I going to do that derivative of this 2x plus 1 to the negative 5th power?
We gotta do another sign.
Yeah, this is going to be my, we'll call it a green, this is my green u in here, and this is my green f, if you will. So df by du green, so we'll call it u2, would be derivative with respect to u2 of u to the negative 5th, which is negative 5 u to the negative 6th, and then derivative of u2 with respect to x is the derivative with respect to x of 2x plus 1, which is 2. Okay. So we can put all that together. So now my levels were, this is my second u in here, and that's my second f out there. So I start with the red one, with the derivative of the outside, which is negative 9 times the inside, all raised to negative 10, and then times, I got to do the derivative of the inside. Well, that's what this says right here. Do the derivative of the inside. Well, that's something minus a 0. So what is that? That becomes, the derivative of that u becomes negative 5 times the u, which is 2x plus 1, which is negative 6, and then times 2. And there's a 0 out here. That's a 0. I don't have to worry about it anymore. So the rest is just maybe a little bit of simplification.
I think this right.
9 and the negative 10 can become, because they're all multiplied, can become a positive 90.
Oh my gosh. Why can't I do this?
That's what I would get right there. I don't know what the book has, but that's what I would get. You must believe it.
Or does it matter which one it is?
Well,
or you said poverty.
I think in this case, because you're multiplying by a constant and by a constant and by a constant, I think it's better to go ahead and simplify that. Now, I can't do any further simplification. I can't distribute this in or anything like that. I mean, that's as far as I can simplify. Other than maybe if you want to write fractions, but I'm good with the negative exponent. Just leave it as negative exponent. Is that what the book has?
I have a question real quick.
And all of that.
Mr. Gaddis.
Okay, hang on a second. We're still got a question here. Just 1 second, Sammy.
It's negative 9. X plus 1 to that's 20.
That's not. I think they're wrong. This is right. Okay, Sammy, you have a question?
With the step with, we had -5 times 2x plus 1 to the -6 times 2. When we multiply the 2 and the -5 and end up with a -10.
Yeah, but the negative 10 and the negative
Yes.
10 times -9 is 90.
Oh, never mind. Never mind.
Yeah. Mr. Gaddis,
Just raise them.
I think the last step was where I got everything wrong for like every problem on 2.4.
Why is that?
Because I got the hind pieces right, but when it came to putting it all together, it just all fell apart.
Things fall apart. Center cannot hold. Well, all I can say is try to keep practice on it. On Wednesday we will do some more examples. We don't have anything new to cover on Wednesday, so you can just practice all the homework. And we can do some more of these chain rules and see if we can get them worked out appropriately. There's homework on Moodle for section 2.6, so make sure you work on that. If I accidentally assign any problems in 2.6, if I accidentally assign any problems that cover the hyperbolics, skip them. I'm not going to cover them. We're out of time. If we had another day, I would do it, but this is the last.
I wish we had another day.
I'll see you on Wednesday. Wednesday.
Yeah. This test is going to be worse. It's going to be worse.
Fruits.
It's gonna be worse than my class.
We primarily do it in joint fitness, but then you'll also be a couple free
You need to jump
I don't know why I'm
on
still
Yes, using your knowledge there as well.
rename it something that's not calculus.
Tuesday is better than Friday. You know what I did while I was in Chapel Hill? I stayed in a filthy apartment in the dark and just went through Tinder with like girls. It was so funny. My girl finally got a match, and the same girl, and the same girl matched with Brandon Miller. And then he was like, "Well, there goes my self-esteem."
Wait, I'm here for Randy.
Yeah, Randy's.
Well, no, wait.
Yeah, I'm like, "You're no better than Brandon Miller, Randy."
He had to learn to accept it.
Right.
And they were like, "It's because he has a beard
This is.
and he's tall." He's not even that tall. Oh, yeah, dude. It was insane. Okay, so in Chapel Hill. So what happened is like in the apartments, you know how there's like a person that lives in the bottom floor underground?
Yeah.
And then there are those windows that like they're at like the top of the wall, right? And they look out.
Yeah.
So, nighttime when there's light inside and it's dark outside, you get a perfect view in. Yeah. The funniest thing was we just saw the waist down. Flaccid. It was crazy. And the funniest thing was, that was it. We didn't see his belly or his feet or anything. It was just.
Oh, is it his dorm?
No, it's not a dorm, it's an apartment.
B to the
We like to think that he was just sitting there contentedly like, yeah, they know.
I would be too.
They know.
I got a video of that.
I gotta record this.
It's just equal to that. Oh.
Amazing. My chapel
So that's
experience
just
was
definitional.
more
You
like
just proved the difference.
we sat down in the classroom where the tour lady asked us
I
many
think we
questions.
should kind of break what you're doing later
Oh, I know.
on.
So I wore them.
Let's go get some food.
It's all black. I got bored. I haven't worn these in like months.
Then what are some like colors?
Finally. So are you coming tomorrow for this time or no? Are you
Josh,
coming?
I don't have to be here till 1:30 tomorrow, and I am so happy about that.
I'm running out tomorrow.
Okay.
Just 'cause
So
I-
at 8 o'clock?
Well, I'm gonna come because Ernest
Where,
is
your
here,
office
but
or?
Yeah, just come by my office. I'll
you
just
just
don't
don't
have
have
to.
to.
And nothing's fine.
Oh, that's a tutor? I missed the last class and. Oh, I didn't.
Okay, let me email everybody. Okay. Thanks. Okay,
I don't know
so
if that-
Josh, Woods, Mason, Sean, Chloe, tell me if I miss anybody, Rizzo, Brittany, which is actually Sarah.
Sarah Robinson.
So there's 3, 4, 8, is there like?
8, yeah.
Did you get Brittany? So we don't have class here tomorrow night.
For sure, that's around 3.
To do homework together?
Just, I need to understand that 2.4 plus 2.5 better.
And help
Is that-
understanding. Oh, those are, you'll get it real quick. Understanding 2.4 and 2.5.
Take a look at my notes, that helps, I don't know, well.
Like I almost actually took notes on it, but I don't know how to approach every problem I see. Like, I don't know what.
Well, your first step is always to try and make FX easier using algebra. Always, no matter what. Like if you have something on the bottom, try to get it on the top so you can use power rule and not quotient rule.
Yeah.
And if you could simplify something, then simplify it first before you start the derivative. That's always your first step. Then, after you get it simplified, then you start using the rules. But the chain rule, I mean, once you get it, you don't have to write it all out like he does. You just keep going piece by piece. And it's easier, I think, if you don't write it out like he does, in most cases.
I don't know what I'm doing times.
Like when you have that U, you don't really need to have that U, you just keep taking the derivative over and over and over again.
Okay.
I think I understand.
I'll try that. Actually, why don't we meet in the lab if it's open, because it has the biggest whiteboard.
Yeah. Nice. It's not like I go through 6 whiteboards. Alright, thank you.
All right, I'll see you in the morning.